as we started the process of determining how we were going to do this webinar, one of the things I tried to think about was one of the questions that I'm commonly asked from customers as I go into plants and work with customers to select the right analyzers for their applications. And one of the questions I'm commonly asked is for the best measurement method for chlorine. But this is a difficult question to answer because there are so many factors. So I thought we could address all the different factors in this webinar today. The best measurement method depends on meeting regulations and, if you need it, for regulatory approval, the application in which the analyzer will be used, sample disposal requirements and availability, the cost of the instrument, the cost of the maintenance, accuracy requirements for the analysis, measurement range requirements, and interferences which exist in the sample. So we're going to evaluate several different EPA-approved methods based on this criterion today. And my goal is at the end of this session, you will be able to identify the best chlorine measurement method for your application. And if you have a method that maybe doesn't fit your application as well as it could, understand how you can apply that more easily and understand what the struggles that you're dealing with may be. And the way we're going to do that is we're going to first discuss why we use chlorine. And then for some background chemistry, we're going to talk about what is colorimetry and how do we use DPD in colorimetry to measure chlorine, the different methods available for chlorine measurement in the laboratory, and the different measurements available for chlorine measurement online or in the process. And then we'll pass it back to Ted for a question and answer session. So there are a myriad of disinfection options available to us, such as chlorine, ozone, UV, and chloramines. But the US EPA requires drinking water to be treated with a disinfection method which has a residual at the water utility customer's tap. So in the US, this limits us to chlorine and chloramines for drinking water. And it's an effective, safe disinfectant for drinking water. It's easy to apply, control, and measure. And you know, I laughed that I put this bullet point up there because we're having a whole webinar to talk about the best way to measure it versus measuring actual chloramines. Chlorine is a much easier measurement to take, a much more cost-effective measurement to take, and an easier measurement to control. Additionally, chlorine is inexpensive, so it meets our goal of meeting public health requirements while still keeping costs low for our plant. The CDC touted chlorine addition to drinking water as the single greatest thing which contributed to the increase in life expectancy in the 20th century. And in 1997, Life magazine called the filtration of drinking water and the use of chlorine probably the most significant public health advantage of the millennium. To set the background and basis for some of our discussion on technology today, I wanted to review the basic principles of colorimetry. Colorimetry is the method by which the majority of drinking water plants measure chlorine both in the lab and online, and it's defined by Beer-Lambert's law, which is pictured here. Colorimetry measures the absorbance of light passed through a sample with reagent that has been added to it. And absorbance is linear over that measurement range. And guys, it's a little difficult to describe colorimetry. Usually when I do this talk, it's an in-person talk and I have some visual aids where we can actually look at the instrumentation and talk about path length. So I'm struggling a little bit on that. And if you do have any questions, please make sure to ask them. To make the reading more accurate, a zero sample should be taken before each reading in colorimetry. And this accounts for any color or absorbance of the blank sample, as well as any fouling or scratches in the measurement cell itself. Different reagents can be added to different samples to identify different species or analytes that we're trying to measure. And these will be measured at different wavelengths. So that's an overview of colorimetry itself. And now I'd like to talk more specifically about DPD chemistry, which is the chemistry that we use to measure chlorine. DPD chemistry is N,N-diethyl phenylene diamine. I think we can all understand why we just call that DPD because it's much easier to say. And it turns the sample into a pink color as pictured here. The darker the pink color, the more chlorine in the sample and the more light is absorbed by the sample, and less of the light reaches the detector on the opposite side of the measurement cell. Chlorine with DPD chemistry can be measured anywhere between wavelength 512 and 553 on a colorimeter or a spectrophotometer. And where that is actually done depends on the manufacturer of the instrument that you're using to measure it. So with that basis in chemistry, we're going to go on to discuss the methods for chlorine measurement in the lab. And I will say, for the purpose of our presentation today, I've included portable methods in the laboratory section of the discussion because these methods can be used in either the lab or the portable, and there's really only one method that I consider a truly portable method, and so I didn't want to have a separate section for that. And the first lab solution we're going to discuss is the colorimetric or the DPD method. When I first started in the industry, many plants used color wheels to monitor chlorine. Color wheels use the human eye and a color comparator disc to determine the concentration of chlorine in the sample. With this method, there was a significant amount of error because everyone doesn't see color the same way. This method also used a blank or a zero sample, like we do today, but the blank sample was not located in the same cuvette as the sample. And so if you have staining on your sample cell or scratches on your sample cell that made the sample look darker, those were not identified in the comparison basis. And so there was a lot of reading error and a lot of controversy over actually doing that with the human eye. The new methods using light and measuring absorbance, as well as zeroing on the same cell in which you react the sample, removes the human error from the equation. Now it's as easy as pour the sample in, push a zero button, add the reagent and wait whatever the appropriate reaction time is, and that depends on whether you're measuring free chlorine or total chlorine, and press a read button, and then we have a chlorine answer. DPD as a reagent can be supplied in push-button dispensers, plastic pellets, or foil packets as a powder. It can also be supplied as a liquid pre-measured as test tubes or in a bottle with a pipette-style dispenser, or even in vacuum-sealed tubes, which suck in the correct amount of sample when you break the vacuum under the water. As far as things to watch for when taking the measurement, watch for and clean or replace badly stained cells. Pouring out the reacted sample and rinsing the cell right after use will prevent cell staining. And I know that sounds like an obvious thing, but as I've traveled, I'll see people that, okay, they measure it, and maybe you're at a distribution system. You take the last measurement in your truck, and then you're going to drive 30 minutes, and the reacted sample will sit in the cell, and that will start to cause color in the cell over time, which can cause error in your reading. Before you take the measurement, we want to wipe the cell outside clean with a lint-free cloth or a chem wipe, and ensure that you put the cell into the instrument the same way each time. There's not really a correct way to put it in unless you do have a scratch or something that you want to avoid being the light measurement path. But we want to put it in the same way when we zero and when we read, so that we're sure that if there is any abnormality in the glass, we're zeroing that out. And obviously, for any optical measurement, we want to make sure that we're not touching the sides of the sample cell before measurement and putting in fingerprints that can also cause issues with that. For compliant samples, and really just for good data and good measurement technique, samples must be checked within 15 minutes of acquiring the sample. And that's not just for DPD, that's for any of the chlorine measurement samples we're going to talk about today, because you can have chlorine lost from the sample, particularly with free chlorine or chlorine that's not complexed. And this is one place where the DPD method really shines because it is a portable method. And if you look at the picture of the one we have here, this is actually HF Scientific's version of it, but lots of manufacturers make versions of a portable chlorine meter. And because you have to measure the sample so quickly, it's very advantageous to have a portable one, particularly if you're working in distribution or if you're taking samples from customers' taps. Since the chemistry and absorbance stay the same over the time and each sample is zeroed before the measurement, this method does not require calibration, but can require periodic verification to ensure correct measurement performance. And I say that generally manufacturers do not require calibration. Please check with your local regulatory body if they do require calibration. But honestly, because it's so difficult to make a good primary chlorine standard, many regulatory bodies have deferred to the manufacturer's recommendation of verification on colorimeters. And the DPD chemistry is available to measure both free and total chlorine, and usually it just requires a change in the reagent and the wavelength is the same. It's not pH dependent like some of the methods that we're going to talk about in the online section. It does require consumables. So there is a reagent that we have to use that we've discussed each time. And so there's a cost associated with that for reagents. And the limited measurement range is usually acceptable for municipal applications, but you can really only measure up to 10 ppm with DPD. The common interferences are permanganate, manganese, and other oxidants. It's actually used, DPD is actually used to measure permanganate and bromine and some other oxidants with a multiplication factor. But if you are using permanganate as a primary disinfectant, then you may want to understand if you still have permanganate left before you chlorinate, because it's going to show up in your chlorine test. The second method we're going to talk about in the lab is the ion selective electrode. And the benefits of this method really come into play if you need to measure high levels of chlorine, so above 10 ppm, or very low levels of chlorine below 0.02 ppm. I often see these used in industrial applications and much less often in municipal application. The relative expense is much higher than that of a DPD chlorine measurement system, but some of these costs can be offset if the meter has multiple probes attached to it, because sometimes you have a multimeter where you can put 2, 3, or 4 probes, and then the relative cost is not as high. It does require reagents both for calibration and to adjust the ionic strength of the sample. Calibration is required daily or as often as you're going to take samples. Certainly if you don't take a daily sample, then you're not required to calibrate it daily. Or at the instance of failure of verification, which must be completed every 2 hours while using the probe. Additionally, this method is more involved and requires some laboratory finesse and good technique to complete the measurement correctly. It's only available for total chlorine and does not have the option to measure free chlorine. And while calibration is required for this method, this manufacturer actually uses iodine to calibrate it instead of chlorine, and that reacts the same with the probe as the chlorine does. So we're not as concerned about making primary standards for calibration here. And I say under the detriments that it's not available in portable forms. Certainly you can take a meter and probe out into the field, but you'd also have to carry all the glassware for your ionic strength adjuster and to measure your ionic strength adjuster, as well as to do your calibrations in the field. And so for me, that makes it not really an option. And the third lab solution I chose to discuss was Amperometric Titration. And previously, Amperometric Titration was performed manually, and it required very good laboratory technique and a knowledge of the millivolt endpoints and the ability to go very slowly as you approach the endpoint of your sample. In the new automatic titration methods, the human error has really been eliminated, and although some sample preparation has to be completed, the procedure is easier and more user-friendly. It does require reagent for each measurement because we're doing a titration, and the upfront cost of the unit itself is the most expensive of the options we will discuss today. But often the instrument can measure free chlorine or total chlorine and even some additional species like chlorine dioxide. Because of the pH adjustment which occurs as part of the process, there are less interferences such as other oxidants which affect this reading. So if you are using permanganate or you have some other oxidants in your system, maybe your primary disinfectant is ozone and it's not all gone before you get to the secondary disinfection, then this might be a good method to consider. The only other thing I would say about this method is because we are pouring and stirring a sample, we want to make sure that we're not creating bubbles or anything that's going to strip the chlorine out of the solution. So it's difficult to perform manually, but when programming the instrument, a very easy measurement to perform. And now we're going to move on to discuss the methods for chlorine measurement online. And many of the technologies are going to be similar, but they have to be applied differently to make the analyzer work well online. In this section, we're going to cover both batch and continuous operation analyzers. But the time required for the batch reaction for a chlorine analysis is very short, so this is not usually a deciding factor in the determination for the best analyzer for a municipal water system. We'll also discuss the upfront cost and the consumable cost and maintenance requirements for each analyzer to help determine the total cost of operation of each. And I'm going to discuss these relative to each other rather than with numbers because there are so many different manufacturers out there that I don't want to leave out a range that I'm not aware of. And most importantly, we'll determine which analyzers fit well in different applications. and where you're going to have measurement challenges with your application. So just the same way we discussed earlier DPD to set the basis for some of the technology, here I want to talk a little bit about how chlorine reacts when we put it in water. It's usually added to water as either a gas or a sodium or a calcium hypochlorite, and then it dissociates to the hypochlorous acid and hypochlorite ion. And this is a picture of the dissociation curve versus pH. And I don't know if you guys can see my pointer. I know yesterday they could. So if we're looking up here at a 6.8, I'm about 90% hypochlorous acid, maybe a little less, maybe 88% hypochlorous acid at this 6.8. If I go over to where I am typically running a water plant, so somewhere around 7.5, I'm somewhere between the 55 to 50% range. And if I go over to maybe a 7.8, I'm dropping below the 30% range. And if I go all the way to an 8.5, where maybe a chloramine plant is running, I'm maybe 12 to 13% hypochlorous acid. And this is going to be important as we discuss the technologies and how they measure hypochlorous acid versus hypochlorite. And the first solution we're going to discuss is the amperometric sensor, or what I've heard called in the industry commonly reagentless. And the standard amperometric sensor design consists of 2 electrodes, an anode and a cathode, and the probe measures the change in current caused by the chemical reduction of the hypochlorous acid at the cathode. Remember, we looked at the hypochlorous acid curve on the previous slide, and we know that our hypochlorous acid, as our pH goes up, significantly decreases. The amperometric sensor was EPA approved in the early 2000s, and the drinking water industry swung strongly in the direction of amperometric measurement, perhaps without fully understanding the technology behind the analysis to look at it and say, does this really fit my sample? Because it came out and it was, oh, it's reagentless. You don't have to use reagents. You can dispose of your sample anywhere. It's going to work great in all applications. And we kind of found out over the years that really hasn't been the case, and there are some challenges with amperometric sensors. Remember that it only measures the hypochlorous acid, so it uses that dissociation curve shown earlier and the pH measurement to determine the percent of hypochlorous acid versus the hypochlorite ion to truly give a chlorine reading that includes both species. And this can actually introduce error in 3 ways. And the first and the most egregious is some manufacturers offer amperometric technology which does not have a pH probe as an option, or they offer the option without the pH probe. Since it only measures hypochlorous acid, changes in the pH of the water will have an impact on the speciation of the chlorine as the pH changes, but the analyzer will not recognize the pH changes. And so the only way for it to give an accurate chlorine reading is if the pH stays very, very stable and you calibrate it right at that point. So any pH measurement changes will cause error in your measurement. The second way I see error is the pH probe must be very accurate for a correct chlorine measurement, and it's very hard to measure pH in a clean sample. So, and I consider surface water a clean sample. Low conductivity samples, it's tough to measure pH in. We do have some surface water where they may not be considered high purity samples, but none of the manufacturers today of amperometric technology, to my knowledge, put a high purity pH probe on their amperometric panel. And this probably has to do with cost, because generally a high purity pH probe does cost more than a standard pH probe, but I believe that it's appropriate for these types of applications. If you don't have a high purity pH probe on there, I would encourage you at a minimum to use buffers made for high purity applications, because what we'll see is we see a lot of drift while it's operating, and then you go in to verify and you put it in a standard, say a 7 or a 10, and it reads perfectly, because pH buffers are very concentrated solutions, and it's very easy for pH probes to read those. But there are high purity buffers that are made for high purity samples that can be used and make that pH measurement more accurate to reduce the error that you're going to have there. And then the third error I really see with this is there can be error in the chlorine probe itself. So unlike the DPD method, it does require calibration, but the commonly recommended calibration for an amperometric sensor is to calibrate it to a spot check on a handheld using the DPD method. But the problem I have with that is it doesn't reset the slope in the electrode itself, it actually just does an offset. So as the curve of the pH or the chlorine probe changes, the changes are not accounted for. And most of this discussion has been around the reagentless version of the amperometric to adjust the pH of the sample. The reagentless, where you use a pH probe to measure the pH of the sample. But I have seen some amperometrics where they do use a reagent to adjust the pH of the sample so that the sample is hypochlorous acid rich. And I do tend to think that those work better. The big benefit of amperometric is that a discharge is not required to go to a sanitary sewer. So for distribution systems specifically, this is often the preferred method. We just want to understand what the challenges are going to be if we need to apply that. It does not require reagents. It does have a wide measurement range, and you can get it in either free or total chlorine options. The same analyzer can't do both, or I haven't seen one that can do both. But you can order either a free or a total, and most people need to measure one or the other. The detriments, as we talked about in the technology, it's very pH dependent, and it still requires consumables, because I think in the upfront discussions, people thought, okay, I get this, I don't need reagents, so I'm not going to have any additional cost for total cost of operation. But you're still going to be required to change the pH probe, to change the membrane on the chlorine probe, or change out the chlorine probe as you have failures. Additionally, it doesn't perform well at low levels of chlorine. So, when we're trying to measure dechlorination or trying to see zero, it doesn't perform well there or in wastewater because you can actually foul the membrane. The common interferences here are going to be chlorine dioxide and ozone and other oxidants. It does require temperature compensation because it uses a membrane, and so how quickly the sample diffuses across the membrane is going to be temperature dependent. The second online solution I want to discuss is one that's probably a little lesser known. It's fairly new back on the market. And the big benefit to it, it's using the ion selective electrode, the same one that we discussed in the laboratory, is it has the ability to measure very low levels of chlorine. The big detriments to it is it's very expensive, both in upfront cost and operational cost, but it's very accurate. And this is typically only used in applications where very low levels must be measured. The maintenance requirements and the reagent consumption are more than those of the other analyzers, but it can be set to measure on different time frames to reduce the requirements of both maintenance and of the reagent consumption. So the detriments would be the higher upfront cost and operating cost, large reagent usage. And it also has very small bore tubing, almost like a laboratory analyzer. And so in the wastewater applications, it tends to have fouling. And the common interferences are iodate, bromine, manganese dioxide, and other strong oxidants. And the last online method that we want to discuss is the DPD chemistry. In the same way we discussed it in the laboratory, there's an online version available of the DPD analyzer. This takes the same measurement that we discussed earlier, and it does not require pH compensation because the DPD reagent already adjusts the pH for the measurement. So it's valid with very low error across a wide range of pH and temperatures. If you select an analyzer which does a zero reading before each sample, because some manufacturers have the ability to do that and others do not, if you do select one of those, it works well in wastewater because the zeroing accounts for some of the cell fouling as you go through the process taking measurements. Additionally, the maintenance requirements on the DPD analyzers tend to be low. It generally requires changing of pump and reagent tubing at an interval like 6 months or a year, and that depends on the manufacturer and manufacturer's recommendations. But it does require monthly reagent changes. And it's important to note that some manufacturers say, well, you can change the measurement time on ours, because a typical measurement time is about 3 minutes on a chlorine analyzer. For instance, ours goes up to 10 minutes, but that doesn't really save you any reagent cost. because the reagents are really only good for 35 to 40 days after you've put them in the analyzer. They'll start to oxidize in the bottle and cause error. So to me, running a continuous analyzer at a batch of every 3 minutes makes more sense than throwing out reagent at the end of the month. The big detriment of this one is because you are adding reagent to the sample, you're going to have a waste stream that goes to a drain or a sewer. And so these can be more challenging to put in distribution systems. The common interferences are the same as those that we previously discussed for the DPD technology. So permanganate, manganese, and other oxidants. And so we talked a lot about the different technologies and where they fit, but I wanted to give kind of a chart or an overview here. So whenever you're purchasing an instrument or selecting an instrument for your application, the key is to understand your application and the goals you want to accomplish with that instrument. And so as a wrap up of these technologies, we can look at what works for drinking water. And it looks like all of these work for drinking water, but then you may say, well, I'm a higher pH drinking water plant. What works there? Or I need to have a sample that doesn't have to go to a sanitary sewer. What works there? I need this very low detection level or high detection level, or I'm concerned with my operations having to learn some very complex instrumentation and I want something that's easy to use. Or certainly if you have to measure a specific species of chlorine, we want to make sure that we pick a technology that can measure free or that can measure total as we need it. So this chart just kind of breaks it down on how to go about selecting the correct instrument for you and try to find one that has the most green check marks that meet your application. So in conclusion, there are a lot of different measurement options for chlorine online made by a lot of different manufacturers, and understanding your application and the limitations of the technology are key to selecting the correct option for your plant. And I wanted to talk a little bit about cost on the previous chart, but I really didn't figure out how to do that because there is such a wide variety of costs from different manufacturers. But what I would say is when you're looking at cost, really understanding the total cost of operations, which means all the consumables. So if you're replacing probes, if you're using reagent, if there is a tubing kit requirement, as well as the upfront capital costs of the analyzer, and understanding, warranty and what does the manufacturer cover as part of that. So I would be happy to discuss with anyone that has questions about their application and help you select the right technology for yours. And here is my contact information. That's my direct telephone line and my email address. And with that, I'm actually going to turn it back over to Ted.
Well, thank you, Julie, for that excellent presentation. Now it's time to answer the questions that our listeners have submitted about chlorine measurement. Remember, you can still submit your questions using the function at the right side of your screen.
So that's a good question, and because there are so many manufacturers, it is difficult to answer, but I can give you some ranges of what I have seen in the field. In general, for a DPD analyzer, you're going to have reagents and tubing kits every year, and you're going to be in that $800 to $1,000 range. In general, for Amperometric, if you have to replace a pH probe and a chlorine probe, a pH probe for Amperometric would range from $300 to $600, whereas a chlorine probe, I would say $700 to $1,200, maybe even up to $1,500. Now, please, guys, don't quote me on these. Don't come back to me and be like, my pH probe is $250, because I probably don't have all of the different manufacturers figured in. But understanding how long your probes in Amperometric last in your application, or looking at the manufacturer's recommendation on when to replace those probes, is key to understanding what those consumable costs look like. In general, in most applications, I find DPD to be less expensive overall, but you can budget for your costs because you know exactly what your costs are going to be, but there may be some manufacturers where it is less expensive. This is going to be specific for each one. In DPD, the differences in testing procedures are there's a different reagent used for free chlorine and total chlorine, and for free chlorine, we want to measure within a certain time frame. I think the reaction time period is 30 seconds, and then we want to measure it within the 30 seconds to a minute after that. For total chlorine, I think the reaction time is 3 minutes. So we want to let it go its full reaction time. But we want to make sure that we measure that free chlorine within that reaction time, or if there is excess DPD in the sample, then it will start to react and you will recognize some of the total chlorine instead of the free chlorine. Online, it's done very quickly and it's done within that time frame, so you don't have to worry about the online analyzer. But when you're doing the handhelds, you want to make sure that we don't, because commonly I'm multitasking if I'm working in a lab, and I might mix something up and leave it for its reaction time and walk away and then come back and measure it. We don't want to do that specifically with the free chlorine. We want to measure it within the time frame specified by the manufacturer of your instrument. For ion selective electrode, we always want to measure the sample within the 15 minutes, but the faster that we can react the sample means less chlorine is coming out of the sample. So once we add the ionic strength adjuster with ion selective electrode, we have complexed the sample, and we want to measure it as quickly as possible always, but less concern than, hey, we've got to measure it right this second. Now, ion selective electrode only measures total chlorine. It doesn't measure free chlorine, so there's not this time period like there is with DPD. For amperometric titration, that was actually one of the concerns I have about amperometric titration, is we need very good laboratory technique because we're going to be pouring the sample and we're also going to be stirring the sample. So we want to make sure that we're not stirring the sample too hard or too fast or creating additional turbulence that's going to strip that out of the water. So when you're measuring free or total there, we're just trying not to lose chlorine. But that's particularly important for free chlorine. That's what you're going to strip out of the sample. So the ideal sample temperature does depend on the technique you're using. For DPD, I think the specifications are between 5 degrees and 45 degrees C. If you are colder than that, you will run the reaction too slowly to react all the chlorine within the reaction time period. So we want to make sure we're at least 5 degrees C for that measurement method. For the ion selective electrode, we want to make sure that we are at the same temperature as our calibration solutions are. So the sample and the calibration solutions, as well as the ionic strength adjuster, all need to be in close proximity. So generally we would say room temperature for this, but because we know we need to make that measurement within 15 minutes of bringing it inside, we may have to use an ice bath or a heater depending on where we're located in the country and the temperatures of our samples to make sure that we're measuring that correctly. As far as the online methods, DPD, again, we want to be within that specification. And also DPD, because we're using typically a cell of some sort, we want to make sure that the temperature between the sample and the air is not causing condensation on the outside of the cell. If it does do that in online analyzers, there are usually desiccants available to put in the online analyzer to reduce the humidity inside. But anything like condensation on the outside of a cell for optical measurement can cause a problem. Because it's an optical measurement, it will scatter light and show up as absorbance. So it can cause the reading to be higher than it should be if there's condensation on the cell for that one. For amperometric, we want to make sure that it's temperature compensated, because as it takes the reading, it needs to figure in how much of the sample is actually permeating through the membrane, and that is temperature dependent. So the analyzer needs to have that math built into it and be temperature compensated. So this is dependent on how there's, like what permutation they are. The dry powders can have a shelf life of up to 5 years, depending on the manufacturer and how they're stored. And certainly for our analyzers, we sell powdered reagents for the online analyzer, and oftentimes the portables and the bench tops are supplied with powdered reagents. But some of the liquid reagents may oxidize in the bottle, as we discussed, like they do after they're mixed. They may have shorter shelf lives. So powdered shelf life in general is going to have a longer shelf life and can be up to 5 years. But for the liquid, it's manufacturer specific on how they mix it.
Okay, the next question is the listener asks, Amperometric Titration lists Pro as low as 0.003 ppm and con 1 to 5 ppm.
I apologize. That's a typo. It should be 0.003 to 5 ppm. So 1 to 5 is with a standard calibration, but you can do a different method in there that goes down to 0.01. So it's still the smallest measurement range that's available because it only goes up to 5 and the other methods generally go to 10. But it will go very low. No, it only reads hypochlorous acid. So it only reads the one species and then it looks at that dissociation curve to determine how much chlorine is in there. So if it's OCl, it's not reading the OCl, it's only reading the hypochlorous acid, not the hypochlorite ion. And then it uses the pH probe to determine what the chlorine actually is. So if you don't have a pH probe on there, it's really lost. It doesn't know where it is on that curve. And that's why I have concerns about using it in the higher pH waters, because in the higher pH waters, we're reading very low levels of chlorine. So any error in that probe is going to make a much bigger error in your actual answer. And the closer to neutral, where it's 88% hypochlorous acid, that's probably an okay application for amperometric technology. You know what? I'm glad you brought this up because I should have included it in my presentation. So in general, if you have high hardness applications, you can often have maintenance issues with the probes because they are membrane. So you can have scaling on the probes, you can have fouling on the probes because they're a membrane probe. And so high total dissolved solids, if they settle out in these smaller measurement chambers, can scale over the probes and cause inaccurate readings with amperometric. Well, I mean, your chlorine is being complexed if you have much higher total chlorine. So it depends on your system. Certainly if I'm chloraminating, I expect mostly total chlorine, right? I don't want to have free chlorine if I'm chloraminating. But if I'm chlorinating and I'm using a lot of chlorine, that's the differential is telling me that it's being complexed with something. So what am I complexing it with? Am I complexing it with TOC and forming disinfection byproducts, or am I actually using it to kill something in that water and it's doing its job and I'm happy that it's doing its job? So it's very application specific and understanding what you're doing, but I'd be happy to discuss that more in a offline and specific to your application. No, well, it depends, okay? We need to dissolve enough reagent to react with all the chlorine in the sample. But DPD is typically bucket chemistry. So if you get a foil packet that says it's appropriate to measure a 10 milliliter sample up to 4 ppm, there's probably enough DPD in there to measure up to 6 ppm. So it depends on how much is undissolved. If it's falling out and the whole clump is at the bottom and none of it's dissolving, certainly I'm concerned with that. But if I see, you know, a grain or two of DPD or of salt left at the bottom, I'm not as concerned with that because it is bucket chemistry. So it doesn't happen with any of the other methods, but if we routinely think that we're going to see over 10 ppm, we probably would want to look at that ion selective electrode method. So I know what we're talking about when we're flushing and we're running very, very high, the DPD actually can bleach out, right? The sample will turn dark, dark pink and then it'll turn clear again. And so I think that's what we're talking about. I don't see those issues with other methods, but if we were routinely running samples in that range, DPD is probably not the right thing to look for or to use to measure that. Or you can dilute your sample, but we want to be careful when we're diluting our sample that we're diluting it with DI water and that we're not creating bubbles and not stripping out chlorine and all of those issues that come with it. So if it's a routine sample that's above 10, I would say you'd want to look at the ion selective electrode mode. No, we always want to, you know, put the cap back on and store them appropriately. And I don't know which ones we're talking about specifically, but in general, we want the DPD reagents capped and stored appropriately. So intermittent flow over the probe generally causes problems And if you were to turn it off and back on, you would need to go out and do verification of both your pH probe, right? Because we're talking about an amperometric in this case, or are we talking about the ISE method? So for amperometric, we would need to go out and do verification that the probes were both working, because dry sample can kill those probes, and they are very flow dependent. So we want to keep a constant flow, and we want to calibrate again if we're going to take the sample off and then put the sample back on. But oftentimes if they're sitting dry, it's going to kill the probes, both the chlorine probe and the pH probe for amperometric if they're not laid up appropriately. For DPD, you actually can allow the analyzer to just not run for some time period and it'll come right back up and run well. For unselective electrode, they do have an intermittent sample option where you can say, okay, I want to run this every 30 minutes. And generally that's done to save reagent cost. I don't know how well it would work with just on-off operation, but some manufacturers, including us, do have a standby option where you can actually send a signal to the analyzer and say, shut this analyzer down and bring this analyzer back on. But you can't do that with amperometric because that's not how it's designed. It does need a constant sample flow.
All right, that concludes our questions. Julie, do you have any very brief final words you might like to offer about selecting a chlorine measurement method?
It's not as simple as it sounds, and it's not as simple as often people think it is. And so I would say, you know, kind of get involved and understand your sample, because this is going to be, as we said, for at least the next 10 years, you're going to have to deal with this analyzer. And you want to make sure that you're selecting the analyzer that's going to be best for your application so that it's not a maintenance nightmare and you're getting the data that you want. If you're spending this money on an analyzer, let's make sure that we get the right thing for your application and that you're going to get the data that you want back from it. And I'd be happy to help and have been in the industry for a long time. So.
All right, thank you, Julie. That concludes our program. We hope you've gained insights that can help you in selecting the best method of chlorine measurement in your facility. If you have other questions for Julie Dawson and the team at HF Scientific, you'll find instructions in the follow-up email that you will receive. Thank you for your participation and have a productive day.